My dear friends, today I am going to explain LCR circuit, series resonance, how it works at resonance. Okay, now we are using AC of this type. It is having some voltage as well as some current. Then AC voltage is given, input is given here. This point is internally connected with this point is connected with this. Now we to measure what is the input voltage which is applied here, input voltage of AC, and that is the effective voltage or the RMS voltage. So we connect this point at here and we connect this point at here. So voltmeter comes in circuit. Now we to connect R, L, C in series. This point is, we connect this point with this point. Okay. Now then we are having option. We may use 250 ohm, 500 ohm or the 750 ohm. It is our choice. If I use this connection further, then I am using 250. If I use this, that means I am using 500 ohm. If I use 750, that this point, that means I am using 750 ohm. Now I use 250. Okay, so this point will be connected here, right? Now then because we are using LRC circuit, R, L and C in series. So this is R. Now comes in inductor comes in series. Then this point will be connected maybe here or maybe here. If you are interested for this capacitor, then don't use this. If you are interested this capacitor, then you connect this point with this point. It is your choice. Okay. So I am using this capacitor. So I will connect this point with this point. Then R, L in series. Now comes the capacitor. It is also in series. Okay. And now this point is already connected in the box. No need of this connection. And this point is coming here, here and here. You have to do one thing. Between the 2 points, connect this ammeter. These are two points for ammeter. One connection will go at here, other will go at here. So ammeter also comes in the circuit. Okay. So all the connections, they are okay. Now then we are coming the least count of voltmeter and ammeter. So here, the 10 divisions, this is 2 volt, then this is 3 volt. Mean 10 divisions equals to 1 volt. Then what is 1 division? That is 0.1 volt. So here the least count is 0.1 volt. Now coming here, this is 0, this is 2 milliampere. Mean 10 divisions equals to 2 milliampere. And what is 1 division? That it is 0.2 milliampere. Now it's okay for ammeter. So voltmeter and ammeter, 10 divisions, 2 milliampere. So this is input voltage is applied here. Voltmeter is connected between the 2 points, this point here. Now then this point will be connected here. Now you may use 500 ohm, you may use 750. Now this is our function generator. Function generator it gives us the AC voltage. Now here that knob, this is a square wave, this is a triangular wave, sinusoidal wave. Sinusoidal, triangular and square. If the knob is here, it is at sinusoidal. The knob is at this mark is at the sinusoidal. So if it is here, then it gives us triangular. It is here, square. Okay, now sinusoidal. Now this is the frequency range. If it is multiplier. So suppose this is at 8. 8 into 1. Now frequency becomes the 8 Hertz. So if it is 10, 8 multiplied by 10, 80 Hertz. 8 into 100, 800 Hertz. 8 into 1K, 8 into 10K, 80K. So this is multiplier. So if it is at 7, now 70K. This reading is 70K. Now this is the RMS voltage. The knob may be at 2 volt or you may have up to 20 volt. And this is the connection for the output. So this is on off button. So this is about the function generator. Now we make the connections. The input is taken, the output of the function generator becomes the input of the LRC circuit. Okay. Now this is our how to make the connections. Output of the function generator becomes the input of the LRC circuit. So it is connected here. Now we do use voltmeter for measurement of the voltage. So I am connecting voltmeter. So voltmeter comes in circuit, right? So it is showing the voltage. The pointer is showing the voltage. Okay. So it is above 3 volt. Now this point will be connected here. Resistance in series. Now I am using 250 ohm. Okay, coil in series. So we are making LRC connection. This is, there is a resistance. First of all, resistance is connected. Then here it is the one end of the inductor. Now at the second end of the inductor, we have connected a capacitor. Look, this is the second end of the inductor. Then we connected a capacitor. Like first of all resistance, then this is coil, then going from here, this is our capacitor. Then all are connected in series. So this is a resistance, coil, capacitor. Okay, then this connection comes here. Applied voltage is between this point and this point. Now between these 2 points, an ammeter will be connected. So ammeter is connected in series. This is milliampere meter. It is connected in series. Okay. Now connections. Okay. Now what we are doing? We'll increase the frequency and we'll note down the current. Now just look. Now the current is very low because the frequency is minimum. This is multiplier. I will just change the knob of multiplier. I'm not taking the full data. I'll just change knob multiplier. Okay, like multiply by 1, then this is multiplied by 10, then 100, then 1. I will change the knob from 1 to this multiply 10, then 100, then 1k, then 10k, then the 100k. Then I'll see what about the current, how it changes. So I'm increasing, just look, further increasing, current increasing, it is further increasing, current now decreased. So current is increased then decreased. So just notice that while increasing the multiplier 1 to 10, then to 100, then 1k, then 10k, what happens here? What happened? The current, first of all, it is increased, became maximum, then it is decreased. This is what is happened. Okay. My dear friends, I am having a circuit. First of all, R is a resistor of resistance R. Then I have connected a inductor of reactance. Inductive reactance means its opposition to AC. It is L omega. Okay, it is called XL, mean inductive reactance. Then I have a capacitor of capacitive reactance XC equals to 1 over C omega. All three are connected in series. Then we have applied the AC voltage. Okay, and this voltage of variable frequency. Frequency is variable. Okay, what will happen? Let that the frequency is omega, and the effective voltage or RMS voltage is EV. So definitely the current will flow. The current which is flowing, it is alternating in nature. The current flowing is of RMS or effective value is IV. IV is the current flowing. What happens? It is giving a resistance L. It is giving a opposition which is L omega. It is giving a opposition which is 1 over C omega. If I ask you what is the total opposition, you will say R plus L omega plus 1 over C omega. But this is wrong. Why? Because no doubt it is inductive reactance L omega. It is 1 over C omega. But you cannot add these reactances in the resistor as it is. You know what is the reason? Because current and voltage, there is a phase shift. Inductor gives a phase shift to the current or to the voltage. Similarly, capacitor also gives a phase shift. There is a phase shift between current and voltage when AC passes through the inductor, as well as there is a phase shift in current and voltage when AC passes through capacitor. So what is the reactance of RLC circuit? So what is the reactance of RLC circuit? The reactance is under root of R plus L omega minus 1 over C omega whole square. You can ask a question, how it is that this formula? Okay, no problem. You go to my video. I will give a link in the description box. Then in that video I explain how this relation comes. Okay, now I am telling you the total reactance of this circuit is square root of under root of R plus L omega minus 1 over C omega square. Now using Ohm's law here, what is Ohm's law? The effective voltage is effective current into this impedance is known as Z. Z is called impedance, mean total reactance of the circuit. So for this circuit, the total voltage between this point and this point is EV. It is equals to current multiplied by the impedance Z. IV becomes EV upon Z. Now what is the value of Z? So IV equals to EV upon under root of R square plus L omega minus 1 over C omega whole square. Now just notice this I will change with the value of R, L, C and omega. Now if R is fixed, L is fixed, C is fixed, then only variable is omega. And you go on changing the value of omega such that if it happens L omega becomes 1 over C omega. What happens then? Denominator here, this value goes to 0 because this equals to this. When this goes to 0, current in the circuit becomes maximum. So the maximum current flows, and that maximum current is EV upon simply R. Then the circuit behaves like a pure resistive circuit. This is called resonance. What is the resonance? Resonance frequency is that frequency at which the two reactances, the value of the two reactances, inductive reactance becomes equals to the capacitive reactance. And in that case, current in the circuit becomes maximum because denominator becomes minimum. And maximum current becomes equals to this. And this circuit behaves like a pure resistive circuit in that case. So this what is happened in our practical when I increase the frequency and I noted down the current. So first of all, the current increases, then it decreases. And this is particular frequency which is called resonance frequency, where the current is maximum. And what is this frequency? You can find it from here. Like L omega is equals to 1 over C omega. Mean omega square is equals to 1 over LC. Mean omega is 1 over under root LC. Okay, and omega is what? Omega equals to 2 pi nu. 2 pi nu is equals to 1 over under root of LC, and nu becomes 1 upon 2 pi and under root of LC. So this is the frequency. You can check because you are having the value of L, you are having the value of C. You find from here what is that frequency where the current becomes maximum. 1 over 2 pi under root LC, and the graph shows whether the graph shows the same frequency at which the current is maximum or not. Then you can verify the frequency, the formula of resonance frequency. Okay.